The activity series of metals helps us predict whether a redox reaction will happen. Some reactions are spontaneous, meaning they occur on their own without any outside help. A classic example: place solid zinc into an aqueous solution of copper 2+ ions. Instantly, zinc loses electrons to the copper ions. Zinc enters the solution as zinc 2 positive, and solid copper is deposited onto the strip. Neutral metals like solid zinc and copper don't dissolve in water easily. That's why plumbing pipes are made out of them. But once the metal becomes charged, it becomes soluble. Try the reverse. Put a strip of copper into a solution of zinc ions, and nothing happens. That reaction is not spontaneous. Spontaneous reactions are energetically favorable. Thinking of water falling, gravity ensures it always flows downward. We never see waterfalls flowing upward, because that would be non-spontaneous. Another example, your cell phone battery. It spontaneously discharges throughout the day. It doesn't spontaneously recharge just from being in your pocket. To recharge it, you have to add energy to reverse the reaction. However, just because a reaction is spontaneous, that doesn't mean the reaction happens quickly. The activation energy might be high, which can make the spontaneous reaction proceed slowly. The activity series ranks metals in order of their tendency to lose electrons. Metals at the top are easily oxidized. Metals at the bottom are least easily oxidized, which means that they are more easily reduced. All entries in the activity series are written as oxidation half reactions. If we want to think about reduction, we have to imagine these reactions running in reverse. For a redox reaction to be spontaneous, the oxidation half reaction must be higher on the activity series than the reduction half reaction. Let's analyze our zinc and copper example. Zinc metal is oxidized into zinc 2+ ions, losing 2 electrons. Copper 2+ are reduced into solid copper. When we find zinc and copper on the activity series, zinc is listed higher, meaning it is more easily oxidized. Copper's reaction is listed in the reverse. Copper 2+ is being reduced by gaining 2 electrons. Since zinc's oxidation is higher on the activity series than copper's reduction, the reaction is spontaneous. Now let's look at the reverse reaction, putting solid copper into a zinc ion solution. Zinc 2 positive must gain 2 electrons to be reduced to zinc 0. Copper 0 must lose 2 electrons to be oxidized to copper 2+. Looking at the activity series, zinc's reduction, zinc 2+ to zinc 0, is higher on the activity series than copper's oxidation, copper 0 to copper 2+. Since the oxidation half reaction for copper is lower than the reduction half, this reaction is not spontaneous. Electrons will not flow from the copper to the zinc ions. No reaction occurs. Here's a practice problem. Pause the video if you want to try it on your own. In this reaction, sodium is oxidized from Na0 to Na+. Iron 2 is reduced from Fe2+ to Fe0. When we locate these elements on the activity series, sodium's oxidation is higher on the activity series than iron's reduction. Because the oxidation half reaction is higher, the overall reaction is spontaneous. Ever notice that your silver jewelry tarnishes over time? That dull dark color is silver sulfide, formed when silver reacts with hydrogen sulfide H2S gas, which is naturally found in the air, and yes, in farts, hence the rotten egg smell. You can reverse the tarnish through a simple redox reaction using aluminum. Line a glass bowl with aluminum foil. Place your tarnished silver items inside the bowl, touching the foil. Pour hot, salty water over it. This reaction is spontaneous, and the salt helps the electrons transfer from the aluminum to the silver. You can use a soft toothbrush or aluminum foil to gently rub the surface and speed things up. The chemical properties of metals often determine how they're used in everyday life. Gold and platinum are very low on the activity series, making them very unreactive. Metals below H+ on the activity series don't dissolve in acids easily. Metals above H+, like magnesium, do dissolve in acids. For example, magnesium will react with hydrochloric acid to produce hydrogen gas. That's why copper pipes are preferred for plumbing. Copper resists corrosion better than more reactive metals like magnesium. Corrosion is a type of oxidation, and iron is especially prone to it. Rust is iron 3 oxide, and it forms when iron loses electrons to oxygen gas in the presence of water. It first forms iron 2 hydroxide, which further oxidizes into iron 3 oxide. The problem with rust is that it flakes off, exposing fresh iron underneath. Over time, the entire object can oxidize and fall apart. But oxidation isn't always bad. For some metals, it forms a protective outer layer. Aluminum, like in soda cans, naturally forms a stable oxide layer that protects the metal underneath. The Statue of Liberty has a green patina from oxidized copper, which is also protective. That's why they don't clean it. The patina helps shield the copper below. We can prevent corrosion with a few strategies. Use a sacrificial anode like magnesium or aluminum, which are more reactive than iron and will oxidize instead of the iron. Galvanized fencing is coated with zinc, which also oxidizes first to protect the iron underneath. These methods are commonly used in fencing, pipelines, and even boats to extend the life of the metal structures.